All right, welcome to our first video lecture. The format of this lecture is PowerPoint slide, and usually it's a little bit different format. If you want to have notes to write on during this video, I did post the slides on Foxtail, and you can print those out to take notes on. All right, so let's get going. We're just going to do introduction to statistics and go over a lot of the terminology that we will use over the course of the semester. So we're going to start off with a couple of quotes. First one by Mark Twain. It says, "Facts are stubborn, but statistics are more pliable." Kind of an underlying implication there is that statistics are pliable and we can make them say whatever we want. And there's a lot of truth to this. Facts are stubborn, something like the sun is going to rise tomorrow. It's not going to change. And it is true that statistics, if they're not done accurately, not done according to the correct procedures, they can be used to say whatever we want. So statistics kind of get a bad rap because that's the case. Just because that can happen doesn't mean that statistics are always untruthful or always bad. And we are having the goal in this class to learn how to do statistics well. All right, another quote, Abraham Lincoln saying 93.2% of all statistics you read on the internet are made up on the spot, which that just kind of just gives us the message in itself. Obviously, Abraham Lincoln could not have said that. And something to keep in mind, when we see a statistic, something that is quoted, something that shows up on an advertisement or an article, we don't want to just believe it. We need to dig in and see what's underlying it. All right, here's another one. Statistics mean never having to say you're certain. All right, this is true because we can't ever be 100% certain when we do statistics, and that is something that we need to keep in mind. If you're presented with a statistic as if it is fact, then we want to be skeptical of that. Okay, but the false part about this is that doing statistic actually requires that we give a measure of certainty. So we may not be 100% certain, but we can be a certain level of, we can have a certain level of certainty. So if you are 100% certain, then you're not doing good statistics. And I would amend this quote to say statistics mean never having to say you're 100% certain. But it's the fact that we can put some measure of certainty on it that makes statistics work. All right, just a quick and dirty definition of statistics. That's the study and process of these three things: collecting data, in other words, taking samples; two, summarizing data. Usually we collect data, we just get lists of numbers, lists of categories, and that has to be summarized. And then the third thing is generalizing from that data about the population that we collected the data from in the first place. All right, an easier way to maybe see this definition is in this schematic. You can see it's kind of a circle, just kind of keeps looping around. Typically we start off thinking about a population that we're interested in studying. So if you kind of start there as the starting place, the population, that is the group that we collect data from, and that then will form that sample. Then that summary part comes in. So when we summarize the data that we've collected in our sample, we get what we call descriptive statistics. That's one branch of statistics. They are just either numbers or graphs that describe the data. Now, this next piece is really what we absolutely have to have good statistics. We need to be able to assess a level of certainty, or we can say it the other way, assess the level of uncertainty that we have. And we can think about that as a probability. We need to have some measure of probability that we use in conjunction with those descriptive statistics to get the other branch of statistics, which is inferential statistics. And that's the branch that allows us to generalize about our population based on the sample that we took. So we're going to go through each of the pieces in this schematic one by one and kind of look at them in more detail. So first one, population. We define what the population is, but we want to define it really well so we know exactly what group, what our sample needs to look like, what group we're sampling from. It can be individuals, objects, measurements. It can be animals, anything that we're interested in studying. So here's some examples. Individuals worldwide, the world population, all George Fox students, all patients on a hospital floor, all trees in a forest, and the list goes on. Now, if we are able to collect data from the entire population, that's referred to as a census, but this is rarely ever done. Even the census that we take in this country every 10 years really truly isn't a census. Not everybody in the United States do we collect data from. There is some estimating that goes on. Okay, so that's population. Now, before we kind of move on to the next part, we want to think about what we're interested in our population. We don't need to know everything there is from the population. There's just going to be some relevant characteristics to whatever it is that we're studying. And we typically call those variables. So just like other math classes, a variable is something that can change. It isn't just one fixed value. So in this context, a variable is a characteristic whose value can change from one member in the population to another. And it can either be a number, which we call quantitative, or it can be qualitative, which is a category, something that's not a number. Okay, so hours of sleep, number of siblings, distance to the store, those are all numbers. If you get data for those kinds of variables, they're going to be numbers. Things like favorite movie, state you live in, color of your hair. Well, those aren't going to be numbers. They're going to be categories. So that's those would be qualitative. All right, so we've got a population and variables. Let's look at a really small population for example purposes, and that is all of you in this course, all Summer Math 240 online students. And let's say the variable that we're interested in is the number of letters in your last names. Okay, that's great. What is it that we're wanting in the end to make a generalization about this population of Summer Math 240 online students? Okay, well, we have to identify what that parameter is that we are interested in. It's going to be a number that describes or measures a population characteristics. And usually it's not a number that we're ever going to know exactly what it is. So being really specific here, usually we're wanting to estimate a mean or a proportion. Those are the two most common parameters that we are wanting to estimate for our population. Okay, the mean is obviously an average, and it's going to have to be an average of a quantitative variable. A proportion is the percentage of a value taken on by either a quantitative or qualitative variable. Okay, so if we look at a population of just the Math 240 online students, it's really small. There's 20. So this is something that we're going to be able to collect data for from all members of the population. So just for example purposes, normally this isn't something that we can do. Okay, so the parameter is in this first part is we're going to think about the mean. So we can look at all of the population data values, all right? They're listed there, 6, 7, 8, 7, 12, etc. And we can calculate a mean, take the sum of all the values, divide by the number of values, and we get 6.4 letters. So that 6.4 is a parameter value. It's the population mean. Usually we do not know this number, but we want to estimate it. Okay, and we're going to get to that in a little bit. All right, just an example of another parameter, the proportion, the parameter of population proportion. This time, let's look at the proportion of sophomores. Okay, so sophomore is a category that goes with the variable class. It's qualitative, but we are able to measure this using a number by taking a proportion. So the proportion of sophomores is going to be the number of sophomores over the total number. So 10 over 20, we get 50%. Again, 50% is a parameter value. We don't usually know this value, but want to estimate it. Okay, so we're going to look at estimating that. But first, we have a few other things to go over. All right, like I've been saying, populations are usually really large. For example, say we're interested in all college students in the U.S. Well, there's 16 million of them. So we would never be able to, get number of letters in the last name for all 16 million. So we don't have access to the entire population, so we can't calculate the parameter of mean or proportion based on the entire population. So we collect data from a sample, just a subset of the population. And then we can calculate the mean or proportion. But if it's based on sample data, we call that number a statistic. So a statistic is a mean or proportion based on a sample. And it's that statistic that estimates the corresponding population parameter. All right, so a sample mean will be used to estimate a population mean. A sample proportion will be used to estimate a population proportion. Okay, so just like parameters, we end up with a number when we calculate a statistic. Okay, so that goes along with this part of the schematic defining statistics. The process of collecting data is called sampling, and it results in a sample, subset of the population, and we can think of the sample results as being lists of qualitative and quantitative data. Let's look a little bit about collecting data. And this is an important piece because the conclusions that we come up with in that last piece, the inferential statistics, are only going to be as good as the data that are collected. And in addition, doing the statistics well. Okay, our goal is to get a representative sample, a sample that shows the same characteristics as our population. You can think of that as you want a cross-section of the population. And the way to achieve a representative sample is to collect a random sample. So if we think about the lowercase letter n as being the number of members of a sample, to get a random sample, we have to have the case where every member of a population has the same chance of getting included in the sample. One way to do that is using a computer's random number generator, and we'll actually kind of look at that a little bit in this class. So every member of the population has to have an equal chance of being selected, and that's what makes for a random sample, which would give us a representative sample. One thing we want to avoid is a convenient sample, where it basically in the name tells you what it is. It's a sample that is really easy to do, but it's just convenient. That it selects individuals that are easily accessible. So, for example, if I was interested in studying all students taking online classes through George Fox this summer, that was my population. But for my sample, I just sampled those of you in stats class. That would be a convenient sample. That would be really easy for me to do because you're all on Foxtail, I am sending you emails, I'm asking you to respond to things. It would not be representative, it would not be random. Let's look at some ways to do random sampling. One is systematic, where you take your list of population members, you select a random starting point, and then you choose and select population members that are the same distance apart in the list. So the way the textbook shows it, choose the 8th individual in the list, starting with the one that was randomly selected. So the little picture shows the first one selected was the second one, and then every 3rd population member was selected to be in the sample. All right, so that's systematic sampling. And that will work if it's possible to list out the entire population. The next one is stratified sampling. That's where you take the population, you divide it into subgroups that we call strata, and then randomly sample from each of those strata. So one thing to keep in mind here is that these strata usually are chosen to represent a like characteristic. So for example, if I took all summer online students and I broke them up into years, freshman, sophomore, junior, senior, and then randomly sampled from each of those 4 subgroups, each of those strata, that would be stratified sampling. Now it's a little bit different when we look at the next sampling method, cluster sampling. Again, we're taking the population and we're dividing it into subgroups that we call clusters. And then we use random sampling to select sets of clusters. So every individual in a chosen cluster is included in the sample. So the difference here between the strata and the cluster is that the cluster isn't necessarily organized around a like characteristic. So instead of maybe choosing by year, maybe we would, if let's say we have an in-person class, and so we have 4 rows of tables, I might consider each row of tables to be a cluster. And then randomly sample, say, 2 of those 4 rows and include all of the students sitting at those 2 rows. Okay, so those rows aren't necessarily organized around, students sharing a certain characteristic, other than they like to sit in the 1st row or the 2nd row or the 3rd row. But, that's not, quite as distinct as something like a year. Okay, so that's cluster sampling, right? Divide into clusters, and then you randomly choose clusters, and all the individuals in the clusters are chosen to be in the sample. Okay, so let's look at the next piece. Descriptive statistics is what we get when we summarize that sample data. And there are 2 different types. We have numerical descriptive statistics. All right, you have a long list there. We've already talked about mean and proportion, but the other ones are ones we're going to encounter this semester. All right, median, mode, range, variance, standard deviation, correlation, coefficient. And then also graphical descriptive statistics can summarize sample data. So we've got the first one, there's a histogram and then a scatter chart. And then there is a pie chart that actually is based on the majors in this class. All right, those are describing data in a graphical, descriptive way. All right, so now let's take and do some sampling from the population of this class, and then our goal will be to summarize it and then calculate some statistics, some descriptive statistics. Okay, so if our goal is to estimate the parameters of mean number of letters in the last name and proportion that have more than 5 letters, we're going to think about taking a sample from our population. So I actually took 5 random samples of size 7, and they're listed there. All right, so that's just the raw data for each of those samples. Now I can summarize those. I'm going to calculate the descriptive statistics of sample mean and sample proportion of sample members with letters more than 5. All right, for each of those 5 samples. So you can look and see that for each of the samples we get different sample means. And for the different samples we get varying sample proportions, sample proportions of names with more than 5 letters. The sample means and sample proportions are varying because of what we call sampling error. All right, we don't expect those sample means to be the same because there's natural variation that results from sampling from a larger population. It's just going to happen by nature. All right, this variation will decrease the larger the sample size. All right, so that's something we want to keep in mind as we go along. The larger the sample, the less sampling error. All right, the other thing that maybe you've noticed here is that the sample statistics won't necessarily equal the population parameter. So if we look at the mean, none of those sample means equal the population parameter mean of 6.4. They are all something different. Now the proportion that we had for number of letters greater than 5 was, I think, 43%, and that does match up with 3 of those that are there. Okay, each of these sample statistics could be used, however, to estimate the population parameter that corresponds with it. But remember, we would have less than 100% certainty in that estimation. Okay, let's look at the next thing here. Inferential statistics. We use the sample data, the descriptive statistics, and some measure of probability to make a conclusion, come to some inference about the population. It has to include that probability, that measure of certainty. So here are some examples of what inferential statistics are that we will be doing. Confidence intervals, hypothesis testing, and regression. Okay, so let's look at a real live study, a real live report, and pick out the inferential statistics that were done. So we've got this study from Pew Research Center. Many Americans believe fake news is sowing confusion. Okay, we're going to find that statistics are often presented in such a way that it's not obviously a statistic. Okay, and not only that, that there is some level of certainty that's implied. So if we just had that headline, many Americans believe fake news is sowing confusion, that is actually a statistic. All right, we want to dig deeper, and if we look at the pie chart, we can match it up and say, they're saying many Americans, well, the pie chart says 64%, say that fake news is sowing a great deal of confusion. That matches up with many. All right, so that descriptive statistic, that proportion of 64% is getting generalized to say many Americans. Okay, so that's kind of one level of digging into it. Now, just because it's not obviously a statistic and certainty is implied, it doesn't mean it's bad statistics. But we know that we need to look for more, we need to dig deeper. All right, we need to look for the number. Like, that's just what we did. We identified that 64% goes with that word many. And we also want to look for the measure of certainty, and we also want to look at the sample size. And those are the things that are going to help us have confidence in this generalization that's being made, this inferential statistic. All right, so if we dig deeper in this report, we do find this included, and this is the piece that has all the information that we need to understand the measure of certainty and the sample size. Okay, so you can see there in the middle, there's the sample size is 1,002. Okay, and then the 95% level of confidence is a piece of the inferential statistics and the plus or minus 3.6%. Okay, so let's look at that more closely. Okay, so that many really means that there's a 95% probability that the actual percentage of Americans that believe fake news is sowing confusion is in an interval of values between 60.4% and 67.6%. Okay, so how did I get that? So we go to this plus or minus that's included in the part of the write-up. That is telling us that if we take that 64%, subtract 3.6, and add 3.6, we end up with this minimum value of 60.4, this maximum value of 67.5. Okay, and then the 95% level of confidence tells us that we are 95% confident or 95% certain that the real percentage of Americans that believe fake news is sowing confusion is not equal to 64%, but it is in a range of values, an interval values, where we take 64, subtract 3.6, and add 3.6. So we're able to see like, okay, 64%, that's the sample statistic. And we've already talked about how we know it's not going to equal the population parameter. That 64% is not going to equal the population proportion. All right, so to add certainty, what we have to do is we lose that precision of 64% and we look at an interval around it. And we can add that level of confidence, that 95% level of certainty. And that's what makes the inferential statistic something that we can have confidence in. Okay, so that's basically what we have here is a confidence interval, and that's one of the inferential statistics we're going to be looking at in the class as we go along. Now let's look at, here's our schematic again. Now let's put in the pieces of the schematic based on this report. All right, so the population, all right, American adults. So we collect data and we want to think, what's the sample that they collected? Well, they collected, actually before that, sorry. How did they collect data? Well, if you dig into the report, you find that they made random calls to mobile and landlines. And they were able to interview 1,002, so that became their sample, 1,002 American adults. They summarized the data by calculating some proportions and also creating pie charts. So they had numeric and graphical descriptive statistics. And the assessing uncertainty piece, right, that was that 95% probability and the plus or minus 3.6. And that was the inferential statistic part that allowed, that allowed them to make that generalization, many Americans believe fake news is sowing confusion. Okay. All right. Talking a lot about probability, we have a whole chapter on probability, but I'm just going to, quickly define it here. It's a measure of an uncertainty of an event occurring. It's a likelihood that something will occur. It's going to be a number, something between 0 and 1. And we study that as a part of statistics because it provides that connection between the descriptive statistic and inferential statistic. Okay, just a few more things here. A little more on data types. So we talked about qualitative and quantitative. And we want to actually break quantitative into two different types now. So we have discrete and continuous. Discrete quantitative data, usually we arrive at by counting, and it would answer a question about how many. And discrete data is given to us as a particular set of values that it can take on. Okay, if we look at our list of under what type of data, number of credits, all right, that would go under discrete. And height, actually, all right, a continuous random variable is one that is also a number, usually arrived at by measuring, and usually is answering a question about how much. And it can take on any value in a range. So height, the second thing I have listed under what type of data, that would be an example of a continuous random variable. All right, we might have a minimum height of, something like 20 inches for a human being and a maximum height of, whatever that might be, 7.5 feet. Well, height could take on absolutely any value in that range, and there's actually an infinite number of values in that range from like 1 foot to 7.5 feet. Okay, now we're limited in how precise we can be in measuring height. Okay, So we don't want to think about that part. We want to think of like, well, it could take on any value in that range. Okay, let's look at the rest of the data in this list. Favorite color. All right, well, that's not numeric at all, so that's actually qualitative. Time to take a test. Well, time is something that we measure, so that's going to be continuous. Number of sunny days in June. Something we can count and takes on particular values, right? We could list them all out, in fact. 0, 1, 2, 3, etc., all the way up to 30. Daily temperature high in July. All right, we can't list out all the possible daily temperatures in July, and we arrive at that by measuring. It takes on values in a range, you know, maybe a low of something like 45 to a high of something like maybe 95, and that temperature can, that high temperature can be any value in that range. Okay, we're going to do a little bit of practice now. We've kind of covered a lot of terms, and we want to identify what they are for some particular scenarios. So the study was done to determine age, number of times per week, and the duration of residents using a local park in Portland. The first house in the neighborhood around the park is selected randomly, and then the resident of every 8th house in the neighborhood around the park was interviewed. Okay, the population is, all right, take a second, think about what that might be. In this case, it's the houses or residents in the neighborhood of the park. That's the population of interest. And what's the sampling method? Well, it's systematic since they start with one house and then they randomly, they randomly select the first house and then they randomly chose 8 to go to every 8th house. Duration is what type of data? All right, we have the 3 options: qualitative, quantitative discrete, and quantitative continuous. In this case, we've got quantitative continuous. What about the color of the houses around the park? Well, that can't be answered in a number, so that's qualitative. Number of times per week is what type of data? Well, that's going to be a number, so it's quantitative. And it's going to be discrete because that's something we're asking, how many? All right, here's another one for you to try. So I would suggest you pause the video, read through the example, and identify each of those 6 things. Okay, let's look at this example and identify each of the pieces here. Okay, population. The population is the cardiologist patients who have had heart attacks. All right, so all of her heart attack patients is the population. The sample that she takes and the method that she used. Well, it says she randomly selects 20. So sample size is 20, and she just says she takes a random sample. Parameter of interest. All right, so we want to think about what is it that we're interested in particular for this population? Well, mean recovery period. So the parameter is a mean in this case. And a statistic. Well, the statistic is going to match up with what the parameter is. So it's going to be a mean, and it's the sample mean, and we can actually calculate it. We're given the total recovery time for these 20 patients is 1,400 days. We divide that by 20, we get 70 days for the sample mean. And the variable. What was the variable that we were interested in measuring? Well, that was recovery time in days. And the data type is quantitative. Okay, that wraps up our first lecture. You feel free to go back, rewatch anything that you need to. And until next time, ask questions on the forum if you have them, and get going on the rest of the things that are due on Wednesday. All right, see you soon.